for Professor Karsas for the kind introduction, and thanks Professor Ruth Williams and Alex Maltovich to organizing this workshop and inviting me to give this talk. And so I will talk about numerically solving queuing control problem with Brownian approximations based on neural networks. So this talk maybe has a sort of different flavors with other talks in this workshop. And I need to be nervous to present this thing in front of mathematicians because it really contains minimum math in it. But I really want to get your feedbacks and your reactions. And this is a joint work with my postdoc advisor, Professor Baris Ata from Chicago Booth, and Mike Harrison from Stanford Graduate School of Business. Okay, let's get started. So we want, in this talk, our final goal is to solve the queuing control problem. And perhaps the most important or the most well-known queuing control problem is this crisscross network. So basically, we want to minimize some discounted sum of holding costs, and we need to make a decision at the server 1 whether to prioritize Q1 or Q2 at with different states. And here we are interested in the parameters regime that the holding cost of 1 and 3 is larger than the holding cost of 2. Q is the queuing length of 3 queues. 1, 2, 3 queues, right? Yeah. Okay. So the network goes like that. So for server 1, it can handle both Q1 and Q2, and for server 2, it's handle Q3. And the Q2 first was served by server 1, and it's become a class 3 or Q3 job, becomes served by server 2. Okay, very easy example, right? Actually, so my idea is to prioritize Q1, but not starve the server 2, because if there's no jobs in Q3, the server 2 will be unnecessarily idle. Okay. Yes. The Q2 will go to this class. Yes. Yeah. Leave the system. Yes. Yeah, no, it just leaves this. Okay. Any questions about this example? The protocol, this method. So. Yeah, of course. So you know, the holding cost of Q1 is sort of large. So basically, we want to prioritize Q1, make its access as fast as possible. But if we always doing that, okay, there's a lot of jobs here in Q2, and there's will be empty jobs here. So probably there will be this Q2 will not be stable. It will be blowing up. So when this is Q1, Q2, Q3. Yeah. Oh, sorry. Yeah. This I should say Q1, Q2, Q3. Okay. Anything else about? Okay. This is the simple motivation example, and how do we solve that? So there's 40 years of development of solving queuing control problems. Probably you first develop some heavy traffic theory and develop the Brownian control approximations, which looks like that. And then we perhaps can develop some dimensional reduction techniques and becomes a two-dimensional equivalent workload problems. It's from 3 dimensions to 2 dimensions. Okay. So those type of thing has been developed in the past 40 years. And however, there's still a problem. This is still a 2-dimensional PDEs. We cannot solve that exactly. Okay. So what is our job? So first, we approximate this equivalent workload problems, this 2-dimensional single control problem as drift control problems, and we develop some numerical methods to solve that. And the second one is that we transfer this drift control problem back to this single control problems. Finally, we transfer this single control problem solution to the prelimit previous queuing control solution. So the solution of the queuing control problem. Okay, this is the whole agenda. Anything question here? Okay, let's get started. So this is the content of the day. First, I will show the method to solve the drift control problems, and second, like based on the drift control, this method, we will show how to solve the single control problems. Finally, we will transback those diffusion control solution to the prelimit queuing control problems. Okay. This is the kind of drift control problems we are looking at. Like theta is our controlled drift, and y is the boundary control, so local time, and the z is the state. So we want to minimize discounted cost. So this is cost c with the could depend on the state z and the state z and the drift to control the drift theta, and also some cost of the local time, the boundary control. So theta is controllable, but the y is not controllable in this problem. Okay. Y is like the reflect term, reflecting on the boundary. Yeah, a boundary of the orthant, or some other space. It's really doesn't matter. Okay, and we have the HJB equations. So with some boundary conditions for this problem. And our method is based on this paper. So their goal is to solve high-dimensional PDEs with some terminal conditions. And we just mimic their method, and we can now solve this problem. So a high-dimensional PDE with some boundary conditions. Okay, so what is this method? First, we need to find a nominal control with theta hat. It's predetermined. In our method, we just use its theta hats all once. And we call it a reference process, Z tilde, which is a reference process. And this is a reflective Brownian motion, Z tilde, with a drift, negative drift, theta tilde. And by applying the ETO's formula, we have this thing. The V, you can think about is some value functions. Okay. And if this V is optimal value functions, we know it satisfies the HJB equation discussed in the previous page. So the red part is the HJB equations, and the blue part is these boundary conditions. By plugging the HJB equations into this ETO formulas, we have this reference SD with the key identity. We call it key identities. So here we want to find the value functions and satisfy this key identity. Okay. And our method actually is will be very easy from now. We choose a horizon lines T, and we independent sample n discretize parts of the Brownian motion W. Then construct the corresponding reflected Brownian motion Z hat. It's a purely simulation-based method. Then we just take the difference between the left-hand side and the right-hand side, which is the delta, and make it a square loss. We minimize the delta square for computation here. And one key trick here is that we can parameterize V and the gradient of V with two different neural networks, two different functions. And we discretize everything. So the integral becomes the sum of the discretized version. Finally, if we solve the optimal value function, find the optimal value function and the optimal value gradient, the proposed control will be like that. Okay. So probably one thing, one important thing is that why can we parameterize value function and gradient value function with two different, not really two different, totally independent neural networks. Let's define neural networks. Okay, it's just a parameterized function. It's a function with a parameter theta. Well, it's a function, so it's just f theta x. Yeah, with some parameter theta. Yeah. So we define v equal to fw1, I think z. Yeah, this is some v z, and it's g. Okay. So you can just think of its parameter, it's a parameterized function. Okay. So let me explain why we can parameterize the function function v and the gradient of v with two independent function class. So here is our proposition. If like v is twice continuous differentiable and g is continuous functions, if we have this identity hold almost surely for every starting point z, then we have this v satisfies the previous HB equations, and we have the gradient of v equal to g. So that thing give us the foundations of the previous method. Okay, this is the high-level descriptions of our method, and here we can I can show you some numerical examples. Here is our basic test problem. There are this is so z process like this. We control theta, and the cost function is linear on the z and the theta. The cost of the local time is 0, and the space of the drift is from 0 to b. Okay, and the R matrix, it looks like that. So if you map back to the queuing context, it's looks at this two-stage queues. You have the first stage like Q0, and after finishing service and the first stage, it will be routed to k subsequent queues. Okay. Okay, here are some like properties and features. The holding cost for the first stage queue, the Q0 is 2, and the subsequent queues are all 1.9. The cost for the control is all 1s. The discount rate is is 0.01 or 0.1, and this upper bound for the drift is 2 or 10. So you can interpret it like that. At any time, the system manager can reduce the input rate to the upstream buffer by amount theta 0, or speed up the downstream server by amount theta I. And the optimal policy, if we can solve the optimal value gradient functions, it's become a Bonbon type policies. So it will be either b or 0, and depending on the value gradient. Okay. Okay, here are some choices of the hyperparameters of the computational method, and probably not very important at this stage. Here are our solutions. First, consider the case k equal to 1. It's become the tandem queue case, and we can solve this problem. And this is our solutions. At the red part, the drift equal to b, and at the blue part, the drift equal to 0. It's I think for the first dimensions control, and this plot is for the second dimension control. Okay. And we can compare our method with some simple heuristics. Here we define a benchmark called the linear boundary policies. Basically, we search for a linear boundary. Here, if you saw our policies, this boundary is not linear. It's like non-linear boundary, and but we suspect that a linear boundary with this slope could also perform very well. So we can search for this linear boundary policies. So it looks like that, and we search for 4 parameters, find the U0 and the U1. So here is the best linear boundary policies. You can see that it's really mimic well of our proposed policies. And if we simulate the performance, our policy has a very similar performance to the benchmarks. Okay. And we can also scale up our method to a higher dimension. Here is 21 dimensions examples. We have 1 upstream buffer and 20 downstream buffers. Here we saw that our policy still performs similar to the benchmarks. And yeah, let's demonstrate the performance of our method. So this is our the first part about drift control, and our next part is about the singular control. So basically we will approximate the single problem using a drift control and solve that approximated drift control problem. Okay. So here is singular control problems. We have cost. So it's object function including a cost of the state W, and okay, and a cost of this control UT cost rate is kappa, and the WT is a reflected Brownian motion, but here the reflected term U is controllable. Okay. And this S is a predetermined like space. It could be a positive or orthant, and we must the control must satisfy this constraint. So it's a constraint optimization problem. Okay, R is the reflection direction for each control. We have K controls and I think D dimensions. Okay, so we can approximate the previous single control problem with to this drift control problem. We first pre-specify a reflect directions at boundary. So if there are multiple choices at the boundary at some boundary point, we just arbitrarily choose one, and we select a very large constant B. Then we solve this single like drift control problem. So we control the drift theta. The object function including 2 terms. One is the theta cost, the drift cost. One is the boundary control cost. This Y is not controllable. It's just here to satisfy that W is always in this space S. And here is our reflective Brownian motion W with some controllable drift theta. So now it's become a drift control problem which we can solve using the previous mentioned problems, and I can show some numerical examples, including the very first motivated example of the Chris-Ross network. So yes. That's a good question. So we didn't prove that this method is a good approximations, but we think at least if this reflection matrix is M matrix, it should work. M matrix. If R equal to 0, there's no solution. Yeah, like M matrix. Right. They're like so this single control problems, we assume it at least has a solution. if it has a solution, I think, yeah. 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 It may not be on. Yes. Okay. So we will first tackle this crisscross network, and I will show you another network which has 6 dimensions. So let's go back to this network. Let me maybe explain again. The holding cost of the Q1, this one, is 1 plus delta 1, and the Q2 is 1. The holding cost of Q3 is 1 plus delta 2. Okay. Then this is the equivalent workflow formulations of these problems. The cost function is a little bit weird. It's not monotonic. It's like that, and the process is looks like that, and we need to control this U processes. Okay. So in the literature, there are 5 parameter regimes. The first one is that delta 1 and delta 2 are negative. Basically, this is a case that you can always prioritize Q2, the horizontal this Q. And we are most interested in case 2. We have 4 subcases: 2A, 2B, 2C, 2D. And there are a long line of literature discussing those cases and prove optimality of different policies. So here are some theoretical results and conjectures. For case 2A, basically there shouldn't be any pushing inside the domain. It should be only pushing on the boundary. And for other cases, for 2B, there should has some pushing along this W2 axis. Similar for 2C and 2D. We will show you some numerical results like exactly has this like these features. Okay. Okay. This is the 2A case, which is delta 1 equal to delta 2 equal to 0. So all the holding cost is all ones. And this is our numerical result. It's only pushing at the boundary. This is case 2B. The delta 2 is 0.05. So the holding cost is 1.05. And we can show, we solve this problem. And you see that here is a pushing boundary. Similar things happens, and also, so there are all the numerical results that we produce. Okay. Okay, now we want to map back the previous 2 dimensions single control policies to the 3-dimensional queuing control problems. We compare 3 different policies. The first one is a static priority policy, which may not be good. It's always prioritize Q1. And the second one is the optimum policy. We can solve this as 3 dimensions MDP problems, and we obtain this MDP policy. And finally, we have our policy, which is derived from the singular control problems. So let me explain. Q1 is the queuing length of the Q1, Q2, Q1, Q2, Q3 are queuing length of the 3 queues, and we map is to the workload space, so it's W1, W2. The policy is like that. So if the diffusion policies give you a negative gradient for the first dimensions at the point Q1 equal to 0, then we idle server 1 instead of serving Q2. Okay. And on the other hand, we will prioritize Q1 if Q3 is larger than S, or the gradient of the second dimension is negative. So here we call S is called safety stock, which I will explain later. Now you can think about its tuning parameters. So this safety stock is included to prevent the idling of server 2. So to keep some stocks in Q3. Okay. So probably so here are the simulation performance in this pre-limit queuing network, and you can see that MDP is the best thing we can do, and our proposed policy is quite close to the MDP solution. It's I think we see 1% of difference. Okay, let me show you some policy comparison. So consider case 2B. This is the holding cost. So the holding cost of the third server is a little bit higher than the holding cost of the first two. It means that at some time we want to keep the stock at the Q2 or Q1 instead of Q3. So sometimes we may idle the service in Q2, even if there has some jobs, because the holding cost of Q3 is too high. Okay. So let's consider the case that Q1 equals 0, and we compare our policy, we call it different policy, with the MDP policy. This pivot point means that these two policies match. Basically, you can see that if Q3 is very high, it's larger than 15 probably, we will idle server 1 to keep the stock in Q2. Okay, those stocks means to idle server 1. So those plots give you a sense of what our policy is doing, and how does our policy compare to the optimal policy, MDP policy. Okay. Any questions about its plots? So this is case 2B. Sometimes we may idle server 1 to keep the stock in the upstream queues. Okay. The next case is case 2C. So the holding cost of Q1 is a little bit larger. In this case, we may prioritize Q1 even more often, so at the cost of idling server 2. So here are the policy. Here the dots means to prioritize server 1, and we focus on the case Q3 equals 0. So Q3 equals 0 meaning that there's no jobs for server 2 to serve. So normally we should start to prioritize Q2 to at least transfer some jobs from Q2 to Q3. But since that the holding cost of Q1 is more expensive, at some points we still prioritize Q1. Oh, this should be, sorry, this should be Q1. This is a typo here. Dots means to prioritize Q1 in server 1. Okay, so here you can see the pictures when Q1 is sort of larger than 10 here. Even if Q3 is 0, we probably prioritize Q1. This is the optimal thing to do. Okay. Yes, because we can solve the MDP. This is the optimal solution we can solve. Yes, MDP we solve by value iterations. Yeah. So value iteration. Yes. So yeah, this is not a closed form solutions, but this is the optimal solution. Yeah. Yeah. Okay, and the final case is case 2D, which we have 2 parts. So the holding costs have it's more holding costs like holding costs for Q1 and Q3 both is larger than 1. So here we have two parts. One is Q1 equals 0. We probably want to idle server 1 at some time, and second one is Q3 equals 0. We probably want to prioritize Q1 even at the cost of idling server 2. Yes. No, it's 2D. 2D case. Yeah, case 2B, 2C, 2D. Yeah. Yeah, sorry, that's probably to be confusing. Okay, this is for cases. This cases is determined by the parameters here. Okay, there are the second examples. So this example is this many queues in series, and so one job's arrives and served by the first server, then goes to the second server, then go to the final server. So we consider the holding cost regime is like that: 3.9, 2.9, and 1.9. That means that sometimes we may idling some servers to keep the stock in that server, because for example here the cost of Q2 is larger than Q1. So sometimes we may want to idle server 1 to keep the stock at Q1. Okay, and here are our numerical results, and with a comparison with the linear boundary policies I described previously. So here you can see that if the workload, the Q2 is large enough, we probably want to idle server 1. Similar things happens for other odd dimensions, dimension 3 and dimension 5. Okay. And here are the simulation performance. We compare with policy, which is never idle. If you have some stock to serve, then you serve that. And the linear boundary policies, we search for the optimal hyperparameters in the class of linear boundary policies, and also our proposed policy. Well, our proposed policy is a little bit worse than here, but I think it's within 0.1%. So this is cost. So the lower, it's the better. Okay, and we solved this synchro control problems. The last problem is that translation back to queuing control. In the previous example, like this many queue in series were crisscross. It is a simple way to translate translation back to the queuing control problems, but it's a little bit ad hoc. How about this very more complicated example? How should you do that? The synchro control problems or the equivalent workload formulations, there are the dimensions are 2. There are only 2 dimensions. But this queuing controls, we have 8 queues, I think. 1, 2, 3, 4, 5, 6, 8. So the queuing control is 8 dimensions. So how to translate solutions from 2-dimensional solutions to an 8-dimensional policies is not very easy. Okay. Okay. Now let me revisit. Let me still stick to this simple crisscross network. So this is the Brownian control problem. Z1, Z2, Z3, it's the states after scaling of the queuing length. And we have this Brownian control problem, and we have this U1 plus U2 are non-decreasing. Okay. So U1 plus U2, you can think about this the cumulative idleness of server 1. And the U3 is a cumulative idleness of server 2. Based on this Brownian control problems, we can derive this equivalent workload formulation. Yeah, this is the same equivalent workload formulation as the previous I explained. So here, the translation from the queuing space Z to the workload space is by this matrix M. So M times C give you the workload workload state. Okay. Then I will describe a general idea of the discrete review policy. So the discrete review policies make decisions at time point 0, L, 2L, 3L. It's a discrete time. While L is a review period length. And at each review period, we only work on the jobs that are already there at the beginning of the period. So here we can make L is very, very short. So this thing will not harm a lot if we only work on the stocks at the beginning of this period. And also, this policy requires a notion called a safety stock. So now starve some servers. So in the previous crisscross network, this server, we need to include the safety stock to not starve server 2. We need to have some stocks for server 2 to work to work. And however, if you include this safety stocks, the server may unnecessarily idle if the queuing lengths are less than the required safety stock levels. So there are some problems of this method. Let me further give you a heuristic explanation of this discrete review policies, the algorithm. So we start from the current stock, this three-dimensional stock states ZT, and we lift it to the workload space WT. W equal to M times C. Okay, M is defined here. For the crisscross network, and we solve the different control problems, and based on the value gradient I obtained from the previous slides, we can solve for the target workload in the next period. We call it the W star T plus 1. And we solve the LP linear to place the correct stock into correct queues, correct buffers, and it's a Z star T plus 1, which is the target stocks in the next period. And from ZT to a Z star T plus 1, we need to find an activity plan, basically the policy. Well, which jobs, which queues we should work on at the period, this period. Okay. But there are some issues of these problems. First, this safety stocks cannot be too small. Otherwise, it may starve some series because in each review period, we only work on the jobs at the beginning of this period. So think about this server 2, we have safety stock S. If this S is very, very small, for example, S is 0 or 1, sometimes there's no enough jobs here. The server 2 will be idle, and there are a lot of jobs here in Q2. And secondly, the safety stock cannot be too large. Otherwise, the cost incurred by the safety stock is already very large. So there are trade-offs on these tuning parameters, and sometimes maybe you cannot really perform small using these discrete review policies. For example, there's numerical examples. The review period length is very, very small. It's 0.1. So after 0.1 second, you will make a decision based on the stock based on the stocks on hand, and you see that the discrete review policy is perhaps 10% worse than the optimal MDP policy. Okay. So here is cost. So the lower the better. So now we explore this discrete review policies for a long period of time, but we still cannot make it really perform very well. We now think about why not directly solve the Brownian control problems. So the equivalent workload problem is purely for the dimensional reduction, and we have more powerful computational tools. Probably we can solve the like this 3 dimensions Brownian control problems directly. Okay, so let me remind you about this Brownian control problem. Sorry, this is a typo. Yeah. Okay, and let me. Yes. So this U1, U2, U3 are three controlled processes, and Z must be all positive, with U1 plus U2 are U1 plus U2 is non-decreasing, and U3 is non-decreasing. Okay. And we give a drift control approximation of directly for this three-dimensional Brownian control problems. So we replace U1, U2, U3 by theta 1, theta 2, and theta 3. So the blue is theta 1, red is theta 2, and the green is theta 3. And we have this constraint. So you can see that theta 1, theta 2 can be negative, but the sum of these two should be positive. That's corresponding to the constraint that U1 plus U2 is non-decreasing. Okay. Here, by the heavy traffic analysis, we can set B equal to square root n. And in these cases, in this method, we do not need to specify the safety stock because this B itself can regulate the speed of transferring the stocks from Q2 to Q3. So we can directly solve these problems and plug in the solutions to the prelimit Q network, and this is our policy. Here is prelimit interpretations. So if the optimal value gradient satisfies that the sum of gradient, the gradient with respect to the first dimensions and the gradient with respect to the third dimensions is larger than the second gradient with respect to the second dimensions, then we prioritize the Q1. Otherwise, we prioritize Q2. So that's quite intuitive, right? If this marginal instantaneous cost of Q1 and Q2, the sum of these two is larger than the Q2, we'll probably we want to serve Q1 to lower the queuing length of Q1. Otherwise, we probably want to serve Q2. Okay. By implementing this method, we have much better performance. I think this BCP method can achieve performance that within 5% of the optimal MTP performance cost. Now we want to try even better. The thing that recall in our drift control problems, this boundary control term y1 and y2, we have this normal reflections. Basically, we enforce that vi is non-decreasing. However, it should be like y1 plus y2 is non-decreasing. So y1 plus y2 corresponding to the idleness of the third one. So sometimes if like y1 is increasing, probably we can move some capacity to this Q2. So that's one way like modify the previous method. So when y1 is increasing, we give it oblique reflections to this the second dimensions, this y1t, and vice versa. Okay. That's and we use the same pre-limit interpretations, and this rho becomes the tuning parameters, and here we choose rho equal to 0.5, and we found that this oblique version, so this version, it can achieve a much even better performance. It's only within 1% or 2% compared to the optimal MDP solution. So, and this method is quite generalizable. So for any queuing control problems, you just write down the Brownian control problems and give the similar drift control approximations and solve that. Then you can find the optimal solutions and implement in the pre-limit performance, pre-limit queuing network. It should perform really well. Okay, I think that's the end of my talk, and I'm happy to take any further questions. Yeah.
Thank you very much. Questions, discussion?
Yes, yes.
I got a little bit stuck with the numerics on slide 69, 72, and 74. So on slide 69, we see that the Brownian control policy consistently overestimates 69. You are all the way at the end.
69.
Yes, just a numerical table. One back. Okay, so it was 65, but the but I was like 70, so it was like, but it's a 5 current already. So here you see that the Brownian control problem continuously overestimates the optimal policy, right?
It's not. It has a worse performance than the optimal policy.
Has a worse performance, but in one direction. It's not worse sometimes up and sometimes down. It's always sometimes up.
It's a cost. So our objective is minimize the.
Okay, and then you control it at 72 by taking out one term, the rho y. And there I missed, and that's my question. Why this term? Because eventually you reduce the cost, but you're still far off. So how can I choose, if I were to implement this, how can I choose the red term so as to correct, to approximate your solution better?
You mean rho, or there's two parameters. One is rho, another is b. Okay. B, actually you can compute that. From the heavy traffic approximation, it should be 1 root n. This is something you can compute without any tuning. Okay. And the rho is something you probably need to tune. So in this case, if rho equals 0, it becomes the previous this problem this formation. And we probably recommend like the rho just point minus one like rho is 0.05. 0.5.
No, you missed my point. It felt arbitrary. I had no idea why it should be minus rho y. Like y is not minus rho square y. Y is not 5 rho y.
Okay.
Why should I choose that?
Okay. Because here, why we want to include this term? Because actually, it's the correct thing is the sum of u1 and u2 is non-decreasing. Okay, so when you reflect in this drift approximation, you have y1 itself is non-decreasing. So probably you want to solve you should have like y1 plus y2 non-decreasing. So here the most scientific choice rho is should be 1. But it's become a degenerated case. That's something I don't know how to solve. Or that's why we have this tuning parameter rho, which is between 0 to 1, and the y is not y2 square because motivated by it should be linear, right? It's the sum of y1 plus y2. Yeah.
Okay, so you say it should be something linear and it should be between 0 and 1. So I'm gonna scale it with a parameter 0, 1, and then I satisfy it. And there is no logic in the choice because there are zillions of other functions that could also satisfy that. Not linear though.
I mean, linear should have some logic, but the specific rho, I mean, it's just the tuning parameters. Yeah.
Thanks very much for the talk. So if I understand correctly, what you're trying to do is to approximate what would normally be a singular control at some free boundary by a very large drift control. Is that right?
Yes.
Okay. So I have a couple of questions.
Yes.
In some of your solutions, you had idleness. One thing I think you have to watch out for is that doesn't mess up the heavy traffic condition, that at the level of the fluid model, you're using the right averages. Did you encounter that problem at all? That's the first question.
Okay. So this idoneous should be at the rate little like O of root n. So it will not mix up the fluid approximation. So that idoneous in this fluid scale is 0. But in this 1 root n scale, it has some idoneous. Yeah.
So the second question is, did you try this method on parallel server systems where when jobs leave a queue, they have a choice as to which server they go to?
Can you be more specific of this system?
Well, there's, for example, the Harrison Lopez example. Did you try it on that?
No.
Okay. I would be very
Yeah.
interested if you did try it on
Okay.
that.
Okay.
Thank you.
Thanks.
Thank you, Ruth. More debate,
Yeah.
discussion?
So the I have thank you for the interesting talk. So the running cost function it's mostly like linear, right? So
Yeah.
you try like a general convex function of the state. Also the objective function, it's discounted cost. Have you tried? What about other criteria like a algorithmic type?
That's a great question, and so the short answer is yes and yes, and all methods can handle those cases. The first one is about the cost function. If you remember here, so we need to solve this problem, or probably F. This max the theta transpose the group value gradient minus C. As long as you can solve this problem, then it should be fine. Okay, it's the first thing. And for algorithmic control, like average cost control, it's also fine. We can still write down the Ito formula and the similar reference SDEs, and we can solve the by slightly more modify the loss function. This reference SDEs, you can solve the algorithmic control.
I think there'll be complications because the average cost is, if you look at the HB equation, right? So the cost, there's average cost parameters are known, right? So they usually you need to invoke relative value iteration algorithms and so on.
Yeah.
And okay, if I can ask, okay, so deep learning of these, you aim to solve high dimensional problems. How high can it go?
Okay. That's good questions for this problem. For this cost functions, linear cost functions, we can solve up to 30 dimensions. And if a cost function is a little bit wild post, for example, quadratic cost functions, we can solve up to 100 dimensions. Yeah, I mean, I think we can further scale up, but our efforts stop at 100 dimensions. Okay. Yeah.
Could you go to page 52?
52, okay. Yes.
This looks like a complicated cost function.
Yes.
Is it assumed or does it come from some place?
This is comes from, so this cost function is easy, it's just linear cost. Okay. And we want to we transfer this Brownian control problems to the equivalent workload formulations. Then you need to solve a linear programming, and the solution is this cost function.